The objective of this lecture is to provide the second part of the study of interplanetary orbit transfer. So as stated, this is part 2 of the study. Now previously, in part 1, when we started this topic, we described two concepts. First was an interplanetary Hohmann transfer, and the second was rendezvous opportunities for an interplanetary Hohmann transfer. Now, these two parts that we had described previously essentially formed the middle part of our study, because if we recall that an interplanetary orbit transfer is conceived in three parts. And the first of these parts was escape or departure from a first planet. The second part was the heliocentric transfer phase, and the third part was arrival, or equivalently capture, at the second planet. Now, in that first lecture, the first part of this study, we actually focused on the heliocentric phase. That was the part that these two constructs that we developed previously were focused on. So in this lecture, we are going to focus on the constructs of the first and third parts, which is escape or departure from a first planet and arrival and capture at a second planet. But in order to do that, we actually have to first develop this first approximation, which is really important in being able to apply these constructs to the first and third parts. So this lecture is going to focus on, it's going to be the development of an approximation called the sphere of influence. Now, what is the sphere of influence? The sphere of influence actually allows us to be able to determine which body is the primary body under which of gravitational influence on a spacecraft as it's moving between planets. So that's the key here, is that the sphere of influence is a distance from a body, in this case a planet, where below that distance, or less than that distance, distance from the planet. It is the case that the planet has a larger gravitational attraction than does the sun. So we can think of it this way, that if I have the sun in a diagram, here's the sun, and here's a planet. There's a planet out here. Here's my planet. And the planet, of course, moves relative to the sun. That there is a radius around this planet. And actually, to make this a little bit more tractable, let's move the word planet down here. There's a radius around this planet, the distance away from the planet, where inside that distance, we're going to call that thing the sphere of influence, RSOI. That if the distance of the spacecraft, if the spacecraft is within that distance, so if the radius of the distance of the planet, the spacecraft to the planet is less than the sphere of influence, then the planet has the greater gravitational influence, and outside that distance, the sun has the greater gravitational influence. So if the distance from the planet to the spacecraft is less than RSOI, the planet has a greater influence, gravitational, I should say, gravitational influence on the spacecraft than does the sun. So, of course, on the other hand, if the distance is great of the planet to the spacecraft is greater than the sphere, that radius of the sphere of influence, then that means that the sun has a greater influence. So that's the contrary statement, which is that if r is greater than RSOI, the distance from the planet to the spacecraft, that is, then the sun has the greater gravitational influence. So, but we always deal with sphere of influence in terms of a less than construct, because we want to know, like, at what's the boundary where the planet no longer has the greater gravitational influence. So in order to be able to derive this, we actually have to deal with the following diagram, which is that consider a spacecraft moving under the gravitational influence of both a planet and the sun. So here's what this diagram looks like. If you look at it, you've got the sun here. So here's the sun. I'm going to draw it this way. Here's the sun. Here's the spacecraft, and here is the planet. The planet is here. Now the mass of the sun, I'm going to denote it as m sub s. The mass of the planet, I'm going to denote as m sub p. And the mass of the spacecraft, I'm going to actually denote it as m sub v, because I'm going to call the spacecraft is going to be equivalently denoted as the vehicle, which is v. That's what I'm going to call it. I'm going to call it v. Now, I'm going to denote the position of the vehicle relative to the sun with the notation r sub v. So this is capital R sub v. I'm going to denote the position of the planet relative to the sun as r, and I'm going to denote the position of the spacecraft relative to the planet. I'm going to call that little r. So let's write these down. R sub v is the position of the spacecraft relative to the sun, and then r is the position of the planet relative to the sun, and then little r is the position of the spacecraft relative to the planet. Now, using these three positions, we're going to define the following quantities. R sub v is the magnitude of R sub v, and R is equal to the magnitude of big R, and little r is equal to the magnitude of the vector little r. So these are the distances, respectively, of between the bodies. So this is the distance from sun to the spacecraft. This is the distance from the sun to the planet. And this is the distance from the planet to the spacecraft. Okay, now we're going to use that information to be able to develop these, the rest of these constructs. So you can see from the diagram, if you look back at the diagram here, that the position of the vehicle relative to the sun is equal to the position of the planet relative to the sun plus the position of the spacecraft relative to the planet. So we have that established now. Now what we're going to do is we're going to look at forces respectively on all of these bodies. Now consider the gravitational force forces as follows. First gravitational force is going to be the force applied by the sun on the vehicle. This is the force exerted by the sun on the spacecraft. Second is going to be the force exerted by the sun on the planet. And the third is going to be the force exerted by the planet on the spacecraft. Now, in order to develop these, we're going to use Newton's universal law of gravitation. So, using Newton's universal law of gravitation, we have the following. We have that these forces are given as follows. The first is that the force exerted by the sun on the spacecraft is equal to minus g times the mass of the spacecraft times the mass of the sun, all divided by RV cubed times RV. And that's because if you look back at the diagram, you'll see that the position of the spacecraft relative to the sun is that vector big RV, and its magnitude is scalar RV without the vector. So that's the first force. The second one is the force exerted by the sun on the planet, which is equal to minus g times the mass of the planet times the mass of the sun, all divided by r cubed times r. And the third one is the force exerted by the planet on the spacecraft, which is minus g times the mass of the spacecraft times the mass of the planet, all divided by r cubed times r. Now, let's first consider the force exerted on the vehicle. So then, the force exerted on the spacecraft, which we will denote FV, is given as force exerted on the spacecraft is equal to the force exerted on the spacecraft by the sun plus the force exerted on the spacecraft by the planet, which, if we add the two forces that we have from above, we've got minus g times the mass of the spacecraft times the mass of the sun, all divided by RV cubed times RV. And then the second one is minus g times the mass of the spacecraft times the mass of the planet, all divided by r cubed times, all divided by little r cubed times r. So that takes care of that. Now, you notice that the force exerted on the vehicle, so we can write this actually completely. We can say from Newton's second law, we have that the force exerted on the vehicle is equal to the mass of the vehicle times the acceleration of the vehicle in the inertial frame, which then has to equal these two forces that we just wrote down. Minus g m sub v m sub s, all divided by rv cubed times rv, minus g times the mass of the vehicle times the mass of the planet, all divided by r cubed times r. Now, if we divide through by the mass of the vehicle, so if we divide through by m sub v, that gives us the acceleration of the spacecraft in the inertial frame is going to equal minus g times the mass of the sun, all divided by rv cubed times rv, and then minus g times the mass of the planet, all divided by r cubed times r. And what we're going to do with this is we're going to actually give these names now. We're going to call this AS plus P sub P. A sub S is equal to minus g times the mass of the sun, all divided by rv cubed times rv. And what that is the gravitational acceleration of the sun on the spacecraft. And this other quantity here, P sub P, which is equal to minus g times the mass of the planet, all divided by r cubed times r, that's actually equal to what we're going to call the perturbing acceleration on the spacecraft due to the planet. Now, if you look at that, you'll say, well, why do we call one A and we call the other one P? It's because what we're looking at here is we're looking at what does the effect of the planet have when the spacecraft is primarily under the influence of the sun. That's why we label the first one A sub S and P sub P. Now, if we look at the magnitudes, we have the magnitude AS, which is equal to the magnitude of A sub S, is equal to G times MS all divided by RV squared, and P sub P, which is equal to the magnitude of this perturbing acceleration, is equal to G times M sub P all divided by R squared. So now we can actually use this to be able to figure out an approximation for A sub S. Now we know that R is approximately, we should say RV is approximately R. What do we mean by that? Well, if we go back through the diagram here, you'll actually see that the distance between the spacecraft and the planet is very, very small. So, and that's because R is small in comparison to both RV and R. So what I mean by that is as follows, is that R is much, much less than RV, and R is much, much less than R. So because of that, we can approximate AS, which remember is the magnitude of that acceleration. It's not the actual acceleration, it's the magnitude of it, as follows. A sub S is approximately G times M sub S all divided by R squared. That is, replace RV with R. That's what we did. Now, the next thing is we're going to apply Newton's second law to the planet. So next, apply Newton's second law to the planet. And what do we get when we do that? Well, we get the force exerted on the planet is equal to the force exerted on the planet by the sun plus the force exerted by the planet on the planet by the vehicle, which is equal to, well, let's look at this now. The force exerted by the sun on the planet is minus G times the mass of the planet times the mass of the sun, all divided by R cubed times R. But the force exerted, I'm going to leave this for right now, the force exerted by the vehicle on the planet still has to be determined. But from Newton's third law, the force exerted by the vehicle on the planet is equal to minus the force exerted by the planet on the vehicle. And if you look back, we actually have the force exerted by the planet on the vehicle right here. So this was already given from earlier. So as a result, we can substitute that in, and we get that the force exerted on the planet is then equal to minus G times the mass of the planet times the mass of the sun, all divided by R cubed times R, and then we get plus G times the mass of the planet times the mass of the vehicle, all divided by R cubed times little r. And that plus sign comes from the fact that we just used Newton's third law. Now that has to equal the mass of the planet times the acceleration of the planet in the inertial frame. And that is from Newton's second law. So this is again Newton's second law. So as a result of that, we actually get that the acceleration of the planet in the inertial frame is actually equal to minus g times the mass of the sun, all divided by r cubed times r, and then plus g times the mass of the spacecraft, all divided by r cubed times r. And that can just be flipped around and written as g times the mass of the spacecraft, all divided by r cubed times r, minus g times the mass of the sun, all divided by big R cubed times big R. So let's rewrite that on the other page. So rewriting the last result, what we end up with is that the acceleration of the planet in the inertial frame is equal to g times the mass of the spacecraft, all divided by r cubed times r, plus g times the mass of the sun, all divided by big R cubed times big R. So now we've taken care of that. So now what we can do is we're going to actually subtract these two from one another. So let's subtract the acceleration of the vehicle, acceleration of the planet from the acceleration of the vehicle. So suppose now it is desired to obtain the acceleration of the spacecraft relative to the planet. That is, the acceleration of the spacecraft relative to the planet, which is equal to the acceleration of the spacecraft minus the acceleration of the planet. Well, if I take that and subtract, I wind up getting the following result. So this follows from the previous results, which is the acceleration of the spacecraft relative to the planet is then equal to minus g times the mass of the sun, all divided by rv cubed times rv. That's the acceleration of the that's the first term, and then the second term is minus g times the mass of the planet, all divided by r cubed times r. So, and then we subtract the last two terms, which is the last result that we have at the top of this page, which is g times the mass of the spacecraft, all divided by r cubed, minus g times the mass of the sun, all divided by big R cubed times R. Now we're going to have to simplify this. So let's start combining terms, and we'll be able to simplify this a little bit more. So we get the acceleration of the spacecraft relative to the planet is equal to minus, well, if we start combining terms, we've got g, and then we've got the mass of the planet plus the mass of the vehicle, all divided by r cubed times r, and then we have minus g times the mass of the sun, all divided by rv cubed times rv, and then the last term is plus g times the mass of the sun, all divided by r cubed times r. Now if you notice here, what I did in that last result is I combined the terms that have the I forgot an r here. I combined the terms that actually have the vector little r in them to get that last result. So what we can now do is we can now write this a little bit differently. So we can rewrite this. The last result gives the following: that the acceleration of the spacecraft relative to the planet in the inertial frame is equal to minus. Now I'm going to combine things in such a way that I make this a little bit easier to work with. So I've got r, and then what I'm going to do is, actually let's do this a little differently, which is that we've got minus g times the mass of the planet, all divided by r cubed times r, and then this is going to be 1 plus the mass of the spacecraft, all divided by the mass of the planet, minus g times the mass of the sun, all divided by rv cubed, and then this whole thing is multiplied by r sub v minus, and I've got rv all divided by r cubed times r. So in this last result, we use the fact that m sub p plus m sub v is equal to m sub p times 1 plus m sub v over m sub p. That was the first thing we used. The other things, we basically just factored out the approximations, because if you notice that when we actually do all the combination, we use that fact plus and the fact that r sub v is approximately r. So we use both these facts, because if you actually look in the equations, what I did was I replaced every occurrence of r sub v, the scalar r sub v, with r to be able to get that last result. So now what we can do is we can actually compute this result in yet an even different way, which is that, recall from the start that we have the following result, which is that r sub v is equal to r plus little r. That was from the beginning. So suppose that we replace everything in here now, that r sub v. So we're going to substitute now. So substitute this result into the last equation. I could actually say it this way: substitute this equality, or this equation, into the last result. So if we do that, we actually get the following expression. We get the acceleration of the spacecraft relative to the planet in the inertial frame is then equal to minus g times the mass of the planet, all divided by r cubed times r, times 1 plus the mass of the vehicle, or the mass of the spacecraft, all divided by the mass of the planet. That's that term. And then we get minus g times the mass of the sun, all divided by rv cubed. And then we get r plus, and then we get 1 minus r sub v over r cubed times r. And this last result just comes simply from the fact that we've done all these substitutions, and we've used this last result that RV equals capital R plus little r. So then, when we note the following approximation, so we note that the spacecraft has a much smaller mass as compared with the planet. That is, that the mass of the spacecraft is much, much less than the mass of the planet, which of course implies that the mass of the divided by the mass of the planet is much, much less than 1, which further implies that 1 plus the mass of the spacecraft over the mass of the planet is just approximately 1. So now what we can do is we can drop the term 1 plus mv over mp and just replace it with 1, which winds up giving that the acceleration of the spacecraft relative to the planet in the inertial frame is equal to minus g times the mass of the planet, all divided by r cubed times r, minus g times the mass of the sun, all divided by rv cubed. And then we've got what's left over here, which is r plus 1 minus r sub v, all divided by r cubed times r. Now, what we can do is we can actually write this now a second way, which is that we can look at the inertial acceleration using the original quantities. So we also have the following, which is the acceleration of the spacecraft relative to the planet is equal to minus g times the mass of the planet, all divided by r cubed times r, minus g times the mass of the sun, all divided by big R cubed times r, which is equal to what I'm going to call the acceleration of p plus p sub s. Now this last result comes from the fact that the approximation is that 1 minus RV all divided by R cubed is approximately 0 because RV is approximately R. So as a result of that, that term just disappears. So this term winds up being approximately 0, which is where we wind up getting this result right here. So now what I'm going to do is I'm going to define these quantities a sub p and p sub s. So a sub p is equal to minus g times mp all divided by r cubed times r, and p sub s is equal to minus g times the mass of the sun all divided by r cubed times little r. Now this first term, a sub p, is equal to the acceleration exerted by the planet on the spacecraft, and p sub s is the perturbing acceleration due to the sun. Now, if you look at this, you see that we actually have done two things here. The first thing is, when we did it originally, we were thinking about the primary influence being the sun and the planet being the perturbing acceleration. And then in the second case, we're thinking of the planet being the primary body of acceleration, and the sun being the perturbing body. So we have two parts to this, which is, first, we considered the sun the primary body, and the planet to be the perturbing body. And that led to what we called A sub s and capital P, which A sub s was the acceleration due to the sun, and P sub p was the perturbing acceleration due to the planet. The second case is we considered the planet the primary body, and the sun to be the perturbing body. And that led to these last two quantities, which we called A sub s and, A sub p and P sub s. So now what we're going to do is we're going to actually use this information as follows, which is that we know that AS, which is the magnitude, A sub p, which is the magnitude of little a sub p, is equal to g times the mass of the planet, all divided by r squared. We also know that the perturbation due to the sun, which is the magnitude of this vector ps, is equal to g times the mass of the sun, all divided by r cubed times r, where we have to be careful here, because if you look back, you'll actually see that these vectors are not exactly the same in this case. I've got capital R cubed and I've got a little r in the numerator in this P sub s, so as a result, that's what I wind up getting for the magnitudes. So now, using those two magnitudes, we can actually compute the following, which is that, suppose now we want to know when the following is true. The following condition is true, which is that P sub s all divided by AP is less than P sub p all divided by AS. What this condition actually says is that the terms on the left-hand side say, what is the ratio of the perturbing acceleration of the sun relative to the primary acceleration from the planet? And the terms on the right say, what is the ratio of the perturbing acceleration due to the planet relative to the primary acceleration due to the sun? When this condition is met, we know that the planet is in a position where the planet is going to actually have the greater effect on the the sun will have a greater effect on the spacecraft. So if this condition is met, this means that the sun has the greater effect gravitationally on the spacecraft. Right? Now, if we actually now substitute in all of the results, so substitute in the earlier results for P sub S, A sub P, P sub P, and A sub S to give the following, which is that G times the mass of the sun all times R all divided by R cubed all divided by G times the mass of the planet all divided by R squared is equal to, is less than the G times the mass of the planet all divided by R squared all divided by G times the mass of the sun all divided by big R squared. So now if we actually simplify that result, so let's simplify that result. It gives the following, which is that we get the mass of the sun all divided by the mass of the planet times R all divided by big R cubed is less than the mass of the planet divided by the mass of the sun times big R all divided by little r squared. Now if we rearrange that, so let's rearrange it. We get that R all divided by big R to the fifth is less than the mass of the planet all divided by the mass of the sun squared. So what that tells us is that if I set these equal, so suppose we set these equal, so suppose we set these equal, right? So the value of R such that the above quantities are equal is called the radius of the sphere of influence. And we call that quantity R SOI. So that implies that R SOI all divided by big R to the fifth has to equal the mass of the planet all divided by the mass of the sun squared, from which we can actually solve for the sphere of influence. So therefore, the radius of the sphere of influence, R SOI, is given as R SOI is equal to R all divided by m sub p over m sub s to the 2/5. Now what's really important here is that remember that R is the distance from, it's the distance from the sun to the planet. And that means that the radius of the sphere of influence depends upon R, the mass of the planet, and the mass of the sun. Which makes sense because we're comparing the effect of the planet's gravitational field to the sun's gravitational field. Now, what's important about this last result is that it goes back to the diagram that we had earlier, which is that if the sun is here and the planet is here, So there's the planet. Then there's a radius around this planet, which we call RSOI, which is the radius such that if we're that distance or less away from the planet has the greater gravitational influence. So R less than RSOI implies planet, this way, planet has larger gravitational influence. On spacecraft. And if we're outside of that distance away from the planet, then that means that the sun is going to have a greater gravitational influence. And that is the key result that actually allows us to be able to know when we're actually under the influence of a planet primarily or under the influence of the sun. So this is what's called the radius of the sphere of influence. And this little depiction here, this is the sphere of influence, which I've depicted in 2 dimensions because I'm not going to draw it in 3 dimensions, but that's the basic result. So this is the result that we're going to finish this lecture with, which is that is the distance away from a planet when the planet has the primary gravitational pull on a spacecraft relative to the sun, and once we get outside of that distance, then the sun has the greater gravitational pull. Now, to close this lecture out, this actually is going to lead to the next, what's going to be in the next lecture, which is how we actually use the sphere of influence to be able to construct what's called a patched conic approximation. So the next topic is going to be what's called the patched conic approximation for interplanetary orbit transfer. And we'll get to that in the next lecture.